The latest discoveries from the James Webb Space Telescope and the Flamingo study are sending shockwaves through the scientific community, challenging the very foundations of modern physics. As we peer deeper into the cosmos, it is becoming increasingly clear that the large-scale structure of the universe is not behaving as predicted by our standard model of cosmology. This could mark the dawn of a new era in physics, where emerging findings may soon alter our understanding of the cosmos forever. James Webb, hailed as the most advanced telescope of our time, is now poised to collaborate with Flamingo, a groundbreaking project that could significantly upend the long-standing theories of astrophysics. Flamingo, which stands for Full Hydro Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observations, is the most extensive supercomputer simulation ever conducted in astronomy. Its primary goal is to analyze the development of the universe from the Big Bang to the present day. Global research teams have united in this monumental effort, pooling together the brightest minds and the most powerful computers to create a comprehensive picture of the known universe unlike anything we've seen before. The study examines the evolution of the universe over billions of years, focusing on its current expansion and structure. Each simulation delves into specific regions of the vast cosmos, and the Flamingo researchers then combine their findings to construct an ever-improving image of the universe as it truly exists. The shockwaves began when the first complete Flamingo deep field image, akin to James Webb's deep field image, failed to confirm the existing laws of physics. This startling revelation has led scientists to question whether the foundations of cosmology, as we know them, are based on an illusion. The issue at hand is that much of our understanding of the universe has been constructed on the hypothetical existence of dark matter, a substance that has never been directly observed. Since the 1930s, when dark matter was first proposed, it has served as a crucial element in the simulation of galaxy formation and the evolution of galaxy clusters. These simulations, which include dark matter, have allowed scientists to replicate the large-scale structure of the universe as we observe it today. However, as the Flamingo simulations have progressed, it has become apparent that these models are reaching their limits, suggesting that our understanding of the universe may be fundamentally flawed. One of the earliest signs of trouble was the so-called Hubble tension, a discrepancy between different measurements of the universe's expansion rate. This tension has been further exacerbated by the findings from the James Webb Telescope and Flamingo, leading scientists to reconsider the role of dark matter and dark energy in the cosmos. The Flamingo project not only incorporates dark matter into its simulations but also considers the effects of ordinary matter and new particles, such as neutrinos, which account for about 16% of all matter in the universe. Understanding this ordinary matter is crucial if we hope to gain a true understanding of cosmic evolution. Recent simulations have incorporated new factors, such as galactic winds and the mass of neutrinos, which have significantly improved the accuracy of predictions. Despite these advancements, a universal understanding of cosmology remains elusive. The simulations and the vast amounts of virtual data they generate are like an intricate puzzle, and every new observation from the James Webb Telescope or other telescopes around the world provides valuable input for new simulations and data analysis techniques. The complexity of this cosmological dilemma has driven scientists to the brink of frustration. Never before have so many astronomers and cosmologists openly admitted that they are at a loss, unsure of what the future holds. For decades, the Big Bang theory, which posits that the universe began 13.8 billion years ago, followed by a dark era, was widely accepted. However, recent discoveries by the James Webb Telescope have shown that bright, fully formed galaxies existed as early as 300 to 400 million years after the Big Bang, challenging long-held assumptions about the formation of matter and the timeline of cosmic evolution. The Flamingo simulations have further deepened this dilemma by revealing that the real distribution of matter in the universe does not match the predictions of older cosmological models. Flamingo's images vividly depict the distribution and evolution of galaxies and galaxy clusters, highlighting the existence of a cosmic network, a vast structure consisting of filaments likely made up of both ordinary and dark matter. For decades, dark matter has been used to explain gravitational forces and other effects observed in the cosmos, but the latest findings suggest that these calculations may not be as accurate as previously believed. This has brought alternative theories back into the spotlight. For instance, the modified Newtonian dynamics (MOND) theory proposes that Newton's laws of motion need to be adjusted at very low accelerations, such as those found in the outer regions of galaxies. MOND can explain the observed rotation curves of galaxies without invoking dark matter, raising questions about whether our understanding of dark matter's dominance in the universe has been wrong all along. Adding to the complexity is the issue of the Hubble tension, named after astronomer Edwin Hubble, who is considered one of the fathers of the Big Bang theory. In the 1920s, Hubble observed that distant galaxies were moving away from us, leading to the idea that the universe is expanding. This expansion has been supported by various forms of evidence, including the cosmic microwave background (CMB) radiation, a relic of the Big Bang that provides a snapshot of the early universe. However, as our measurement techniques have improved, discrepancies in the expansion rate have emerged, leading to what is now known as the Hubble tension. In essence, direct observations of nearby stars and galaxies suggest a faster expansion rate than calculations based on the light from the Big Bang. This discrepancy has now been compounded by Flamingo's discovery of a new tension within the so-called S8 parameter, which deals with the distribution of matter in the universe. The S8 parameter describes how clumped or clustered matter is in the universe. According to our understanding, these observations should align with the cosmic microwave background radiation. However, recent measurements have shown a shift in the S8 values, indicating another significant discrepancy in our cosmological models. This further complicates the already contentious issue of the Hubble tension, creating a puzzle that scientists are struggling to solve. The connection between the S8 tension and the Hubble tension can be illustrated by the analogy of a balloon. As the universe expands, it is like blowing up a balloon with a dot on it. The dot, representing matter, changes as the balloon expands. The S8 values describe this expansion and the behavior of matter within it, while the Hubble tension reflects the speed and regularity with which the balloon itself expands. If the observed distribution of matter and the rate of expansion don't match the expected values derived from the early universe's conditions, it suggests that something fundamental in our understanding is missing or incorrect. This realization has put cosmologists in a difficult position, as they now face a cosmic puzzle that seems increasingly unsolvable with the current framework. Scientists are feverishly searching for answers, driven by the potential to unlock a deeper understanding of the universe that could redefine the field of physics. The stakes are high, not just in terms of recognition and funding for those who might solve these issues, but also because of the profound implications these discoveries could have on our understanding of the cosmos. As researchers delve deeper into this dilemma, they are revisiting every assumption and model that has been built over the decades. They are questioning whether there are forces or types of matter we haven't sufficiently considered or even completely new factors in the universe that we're only now beginning to discover. The complexity of this task cannot be overstated. Imagine trying to predict the weather on Earth, an inherently chaotic and complex system. Now magnify that complexity to the scale of the universe, spanning billions of years and light years. It's a monumental challenge, requiring calculations and predictions that stretch the limits of our current technology and understanding. In this quest, dark matter remains a prime suspect, but scientists are also scrutinizing other elements of the cosmic equation. Ordinary matter, which includes the matter that makes up stars, planets, and everything we can see, interacts with a range of forces, including gravity, the pressure of gases, galactic winds, supernova explosions, and the activities of enormous black holes. Additionally, there is growing interest in the role of neutrinos and other highly charged particles that traverse the cosmos, potentially influencing the behavior of galaxies and the larger structures they inhabit. The universe, it seems, is a complex interplay of forces and elements, much like the ecological dynamics of a thriving ecosystem. Just as it would be impossible to fully describe the intricate processes of a meadow using a few mathematical equations, so too might it be impossible to completely understand the universe through our current scientific means. We may need to prepare for the possibility that the cosmos is an unpredictable system, one that may never be fully deciphered. Yet, this uncertainty is also what makes this moment in science so exciting. The discoveries made by the James Webb Telescope and the Flamingo study are not just shaking up our existing theories, they are opening up new avenues of inquiry, new possibilities for what the universe might be and how it came to be. As more data is gathered and new theories are developed, we may find ourselves on the cusp of a scientific revolution, one that could change our understanding of the universe in ways we can't yet imagine. These advancements also underscore the importance of continuing to push the boundaries of our technological capabilities. The James Webb Telescope, with its unprecedented ability to peer into the distant universe, is just the beginning. As we develop new tools and methods for observing and simulating the cosmos, we will undoubtedly encounter more surprises, more anomalies that challenge our understanding. Each of these discoveries brings us closer to the truth, even if that truth is far more complex than we ever anticipated. As we stand on the threshold of this new era in cosmology, it is clear that the journey ahead will be filled with challenges. The Flamingo study and the observations from the James Webb Telescope are revealing a universe that is far more intricate and mysterious than we had imagined. This is not just a crisis for physics, it's an opportunity. An opportunity to re-examine old assumptions, to develop new theories, and to expand our understanding of the cosmos in ways that could fundamentally alter our perception of reality. In the coming years, as we continue to explore these mysteries, we may finally begin to unravel the true nature of the universe. It is a task that will require all of our ingenuity, all of our technological prowess, and all of our curiosity. But if history is any guide, the rewards will be worth the effort. The discoveries we make could not only change our understanding of the cosmos, they could change our understanding of ourselves and our place in the universe. The James Webb Telescope and the Flamingo study are revolutionizing our understanding of the universe, challenging established cosmological models, and paving the way for a new era in physics. The cosmic mysteries they're unveiling could redefine our place in the cosmos. The journey ahead promises groundbreaking discoveries that will reshape our view of the universe forever.